All right, keep it going. Here we go. Roll, 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 roll 'em, roll 'em, roll 'em. Oh, in the last video at the very end of it, I said it has a density of 1. You all know what it is in my brain. That was, yeah, no. No, so hydrogen was in my brain, but it's a massive one, not a density of 1. Hydrogen's density is 0.0899 or something like that. But you all know what I meant. Or maybe not, I don't know. So yeah, but the density is certainly going to be an intensive property because it doesn't make any difference how much you have. I tell you I know the density of something is 11.3, then you go, oh, lead. Yeah, okay, moving on. What do we got on this list? International system, I did an entire video just based on that. Okay, that we'll move past that one. Mass versus weight. Mass versus weight. Now we know mass is now not a measure of the amount of matter. Mass is a measure of inertia. Thank you. Thank you, Billy. Appreciate it. All right, so mass versus weight. They're not the same, although they're used interchangeably. Oh, that's not good. Well, that's a bunch of garbage. Dead. Yes, score. Dead. Chalk up one more marker. All right. Here we go, try again. Mass versus weight. Mass versus weight. Okay. If you weigh 195 pounds on Earth and you decide to teleport yourself, blink, like a blink of an eye, like I Dream of Jeannie back in the 60s. She was able to just blink. She used to do this. She'd go blink, and then she'd disappear. Let's say we could do that. Blink. And now I'm on the moon. Would I weigh 195 pounds? No. You know that. You weigh less. You know that. Because there's less gravity. Don't say no gravity. Please don't do that. The moon has gravity. Okay. There's no gravity on the moon. Yes, there is. Okay. It's 1/6 of what it is on the Earth, but there's gravity. What would I weigh on the moon? I will weigh 1/6 of what I weigh on Earth because it only has 1/6 of gravity. So weight has something to do with gravity. This one has something to do with gravity. This one does not. Mass has nothing to do with gravity. So no G, no gravity. What would my mass be? If I were to, let's say my mass is about, I don't know, it's about 95 kilograms. If I were to mass myself, well, 95 kilograms here on Earth. If I go to the moon, what would my mass be? Very good, Barbara. 95 kilograms. My mass isn't going to change, but my weight will, because the weight is dependent upon gravity. Yeah, you did know that. I know you know that. So gravity has something to do with weight. Is it possible to be weightless? Is it possible to be weightless? Yeah, the astronauts are weightless when they're in the space shuttle and they're... Space shuttle, no, it's gone. It's been gone for like 90 years, so forget the space shuttle. Scratch that. International Space Station. Okay, good, we'll use that. And yeah, International Space Station, I've seen those astronauts like in movies and footage and stuff, and they're weightless. They're floating around. They're weightless. No. They're not weightless. In fact, they have just about as much weight as they do on Earth. If you look at the Earth, here is the Earth. Okay? No, the Earth is flat. You're wrong. We're going to have fun with you. If you think the Earth is flat, I like you people. It's so much entertainment. Here's the Earth. Nice and round. The International Space Station, in relative to the size of the Earth, is about that far. You see that? You see that little X up there just above the Earth? It's like 210, 220, 30 miles. It's not very, 200 and something miles. Well, the Earth is really big. Okay, its radius is 6,300 kilometers, which is 4,000 miles. So 200 miles, 4,000 miles, you're only that far above the Earth. You're really not that far when you look at it in perspective of the Earth. There's plenty of gravity there. In fact, we know there's a crap ton of gravity there because the moon is way up there, and that has gravity the Earth is pulling on that with its gravity. So down here, you basically have almost all the gravity that you would have at the surface. So are they weightless? No, not even close. If I go up the International Space Station, I would still weigh probably about 192 pounds. I mean, 103, maybe I'm gonna lose a little bit of weight, but in terms of, but I'm still gonna be almost the same weight as I have. Well, I've seen them, they float around and stuff. Okay, that has to do with different forces and free falling, and it's like, if you're in physics, you'll get into that, okay? But you are not weightless here. Oh, well, where would we be weightless? Good question. Where would we be weightless? In the middle of absolutely deep space. If you were between the sun and the next closest star system, Alpha Centauri, the Alpha Centauri, Proxima Centauri, those stars about 4 light years away. If you're in the middle of nowhere between those two, yeah, there's essentially no gravity pulling on you anymore. In that case, you'd be weightless. So you have to have no gravity to be weightless, which is not the case when you're in space around the Earth. Okay, still gravity there. Just looks like you're weightless. You ain't. So, is it possible for you to be massless? Can you have no mass? Nope. If you have no mass, you don't exist. Remember, any matter, and you are matter. You matter. You matter. You do. Stop it. You matter. You're important. Okay? Pumping you up. You are matter, then you have to have mass. All right. So mass versus weight. Mass from place to place in the universe would not change. Your weight would change depending on the gravitational pull on your body. All right, moving on. What we got next on this sweet list? Some people just check things off as we're going along. All right, you just go, all right, check off. Star Trek, check off, remember? Ensign Chekhov, the Russian guy. Yeah. I like Star Trek. Okay, temperature scales. Different temperature scales. You have Celsius, Kelvin, Fahrenheit. The first one actually was Fahrenheit. The first accepted temperature scale from a lot of people all over Europe. Daniel Gabriel Fahrenheit, at the time, was actually living in Germany when he developed his temperature scale. And the temperature scale of Fahrenheit. So what I'm going to do is make a grid here so we can compare our 3 temperature scales. And let's make, okay, here's our temperature scales. Fahrenheit, and here I'm going to write BP H2O, boiling point of water. And we'll put a grid there. FP of H2O, or MP, freezing point and melting point are the same thing. Some people don't realize that. What's the freezing point of water? 32 degrees. What's the melting point of water? I don't know. 32 degrees. Okay? It's the same thing. And then boiling point and what we consider condensation point are also the same temperature. So freezing point of water. And down here, I'm going to put absolute zero. Absolute zero. So ABS 0. And some of you might have heard of absolute zero. Some of you might not have. And so we have to go, what is absolute zero? And I know some of you are thinking right now, this guy here making these videos, he's an absolute zero. Okay, that might be true, but that's just so mean, okay? Mean. I'm sad. All right, so now, Fahrenheit. Fahrenheit, boiling point of water. A lot of people don't know this one. You know freezing point. Let's do freezing point first. 32. A lot of people know freezing point, melting point is 32 degrees. You know that because we deal with it on a daily basis, especially up here. I know, weather in the winter time and even in the spring or fall, 32 is an important temperature. Freezing point and melting point of water. Boiling point, 212. 212 degrees. All right, absolute zero. I'm going to come back to this one. All right, this is negative. I'll have to describe what absolute zero is. Negative 454 degrees. You don't have to know the exact number here, actually, but you should know that's really cold. I mean, if it's 10 degrees above for zero, it's cold out. If it's 0 Fahrenheit, really cold. If it's negative 10, I don't want to be out there very long. Negative 454? Whoa. That's like Antarctica temperatures. No, actually, it's not. It's a lot colder than Antarctica could ever hope to get. Anyways, really, really cold. Oh, and absolute zero. Absolute zero, what it means is it's so cold that no motion of any kind on any level. So all molecular motion would stop. It's just so. Thank you. Thank you very much. That was my absolute zero demonstration. Next show, 4 o'clock. Tell your friends. Okay. Yeah, so everything, there'll be no motion whatsoever. And there's a lot of reasons why you can't get to absolute zero, but it's a theoretical number. But we can get close. In the lab, they've actually come within one, I think last time I looked, it was like 1/5 billionth of a degree. I mean, at that point, I'd call it a day and say, we got it. But technically, no, you don't. You never can. Okay. But it's really, really cold. Absolute zero, all molecular motion ceases. And you remember, actually, temperature is an indicator of what molecular motion is. The higher the temperature, particles move faster. Bzzz, hot, 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 cold, 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 cold. Yes, molecular motion has something to do with temperature and vice versa. Okay, next one. Fahrenheit. These are weird numbers. So Celsius comes along. Celsius, also known as the centigrade scale. Centigrade and Celsius are the same scale. But Celsius was the scientist who developed the next accepted scale. He said, oh, you know what, this is great, Fahrenheit. Nice job. You have some definite temperatures, and there's reasons why he picked these temperatures were done. One was the lowest temperature you could get with a freezing mixture of ice and salt, and there's different reasons. One was like close to human body temperature, whatever. But the point is, these are just kind of weird numbers. And if you want to look up why the numbers are weird, you can go ahead and do that in a separate video. Okay? It is kind of interesting, actually. Celsius says, I got this. Here's what we're going to do. We're going to actually base the same things, freezing point, melting point, and absolute zero. We're going to do this. We're going to have numbers that make some sense. We're going to start with the freezing point of water will be assigned a 0 degree temperature. Boiling point will be assigned a 100. So on his thermometer, what he did is he took a thermometer, a glass and some mercury at the time, and placed it into freezing an ice bath of ice and water. It wasn't an ice bath. Hello, ice and water. And he marked on his thermometer, etched in, and said, okay, that's the 0 point. Now we're going to take this thermometer and we're going to put it into boiling water. And that mercury is going to go up the column, okay, of the glass. And when it stops, we're going to etch there and write 100. And then we're going to put 99 equally spaced degrees in between. We've got ourselves a thermometer that measures 0 and 100. It makes it, actually, the truth be told, here's a little fun fact for you. Originally, Celsius, and nobody knows why, he never really explained it. He actually had it the opposite. He originally said freezing point of water 100 and the boiling point of water is 0. It's kind of weird, and the Academy of Sciences eventually just went, this is nonsense, we got to stop this. Let's just reverse these. We don't know why he did that, but he did, and we reversed them. So 0, 100, negative 273. Negative 273. All right. Next, Kelvin comes along. Kelvin, mid-1800s. Kelvin and I always say, it's a good thing that there wasn't a scientist who developed a temperature scale in between Fahrenheit and Celsius, whose last name began with the letter U, Ulysses. Okay, if Ulysses developed a temperature scale and I was doing this, that would be kind of awkward. Okay, you don't see it? Okay. You'll get it eventually. Moving on. All right, so Kelvin says, great job, Celsius, great job. We've got some normal numbers in here that are easy to remember. Here's a problem, though. Problem. Celsius is like, what, dude? He was dead already, but he said, what, dude? And Kelvin says, dude, we can't have any of these negative numbers for our gas laws to work. Okay, where our gas laws to work. You know, Boyle's law, Charles' law, those gas laws, they don't work with negatives. So we need to get rid of the negatives. We need to start at 0 and work our way up. Absolute zero is Kelvin starts at 0. And then he kept the same temperature degree gradient as Celsius did. 1 degree Kelvin change is 1 degree Celsius change. They are the same temperature change for degrees. They just start at a different spot. Freezing point of water, you got it. It's off by 273. You see 0 and 273. are off by 273. So this is going to be on the Kelvin scale, 273. Water boils, or water freezes at 273 Kelvin. I go, what the freezing point? Add 100 to this. We're off by 273. That is not a good looking 3. There we go. So 373 is the boiling point of water. 273, freezing point of water, 0. So you add or subtract 273. Actually, it's 273.15 for those of you who are those really anal retentive people out there. I have to be more exact. 0.15. I'm not going to worry about the 0.15 in this class. So add or subtract 273 is how you get back and forth between Kelvin and Celsius. And we will have to do that multiple times. So 273, remember, and Kelvin's bigger. Okay. Whew. All right, we have one more video before we get into international system and dimensional analysis, and I will do that video next.